So, good morning to all of you. So, welcome to the lecture on the subject of power electronics, and the topic of today's session is switching characteristics of SCR. So, I think this is applicable for all the thyristor switches. The switches. In the group of thyristors there. So, let's see the here. Okay. So this is the switching characteristics of the SCR, and it will be somewhat similar to all the switching characteristics what we have discussed in BJT, MOSFET, and IGBT there. So the same thing happened. They say approximately it will be somewhat. Uh, it resembles like the same operation in SCR also. Okay, let's discuss one by one. And before that, okay, so I have added this switch symbol and as well as the representation, the layers representation in SCR. Okay, so I hope you know this. What are the terminals of SCR? So that is anode, just denoted as A here, cathode K, and gate terminal. And this is how the layers are appeared in the SCR. That is a PN and PN, 4 layers, 3 junctions. So that is junctions J1, J2, and J3. Okay, so with a gate control. Okay, so here we have placed a switch to allow the gate current here. So actually this is forward blocking state. Okay, so when anode is positive here and cathode is negative here. Okay, and junctions J1 and J3 are forward biased, and junction J2 is reverse biased. Okay, so of course there exists a small leakage current here, and it is in blocking state. So here nowhere the gate current is applied. Okay, so this is the forward blocking state. Now we have to make this switch to turn on. Okay, so what is the mostly preferred method to turn on this switch? So that means to turn on the SCR means, so by allowing the gate current. So we have to allow this gate current. Okay, so that is the mostly suitable method. Okay, so of course many turn on methods are available, so which will be discussed further. But right now, so the most suitable method is by allowing the small amount of gate current. Okay, so I repeat once again. So initially it is in forward blocking state. Okay, oh sorry, yes, initially it is in forward blocking state. Junctions J1 and J3 are forward biased, and junction J2 is in reverse biased. Okay, and there is no gate current. Now let's look into the operation. So look at the first figure here. So all the x-axis represents the time period in microseconds. Okay, so most probably it will be in microseconds only. Uh, Next, on the y-axis represents the anode voltage, gate current. Okay, and the second figure represents in the y-axis as anode current. Okay, and the loss is about, and the last figure is about the power losses. So this is not much more focused here. Let's look into these first two figures. Okay. So initially what is so as we have discussed when the switch is in forward blocking state. Okay, so now our objective is to make the switch turn on. So that means we have to bring the SCR to from the forward blocking state to conduction state, forward conduction state. Okay, so that is the operation required. So for that, so initially the anode voltage is high. It will be around 100%. So that depends upon the operating voltage. So initially the voltage is VA. Term it as VA. Okay. So here it is VA. So OA represents the initial anode voltage. So here it is OA. So where VA is the initial anode voltage. So this is the maximum voltage. So which is applied across anode and cathode. Okay, now we are slowly injecting the gate current. So of course we have seen the configuration also, how we are so what is the circuit configuration of this SCR. Okay, so through the supply voltage through the another source we are allowing the gate current. So look at here. So through this gate current, sorry, this gate current is injected to a P layer. Okay, so here the junction J2 is in reverse biased. Okay, so look at here. So look at the first figure. So slowly when the gate current is increased, so it will be around very minimum value, minimum gate current here. Okay, so uh, this is the first thing what we are going to do. So when the supply voltage is given, that means when the voltage is applied between anode and cathode, it is in forward blocking state, and now we are going to inject the gate current. Okay, so here now it is segregated into three different intervals and the time period. Okay, so soon after applying the gate current, so there exists I mean it can be subdivided into three intervals, that is delay time, rise time, and spread time. It's not peak time, it's a spread time. Okay, that's fine. I'll use the pointer. So this is a delay time, rise time, and spread time, TP, TD, TR, and TP respectively. Okay, so how can we define the delay time means? So we can define in terms of anode voltage, gate current, and anode current. So delay time can be represented either in anode voltage, gate current, and anode current. So as we have uh, discussed in the BJT, MOSFET, or IGBT, so the same thing we here similarly here also we are going to define. So delay time. So in terms of anode voltage means the time taken for the anode voltage to reach from VA to 90% of VA, or the time taken for the anode voltage to reach from, so this is the maximum value, so it can be treated as 100%, or you can term it as VA to zero point 0.9 VA. So this is the total time period for the anode voltage. Okay, so because if we consider practically, so here we are going to turn on the switch, so immediately turn on and turn off, it's not the case. So there exists the partial turn on and partial turn off. Okay, so immediately it cannot get into the maximum value, so there exists a decaying or exponential rise likewise. So hope you know the reason. So because of its junctions here, so you look at here, it requires some transition time, okay, to get into the saturated. Okay, so in terms of gate current, if you want to define means, so the time taken, so I'm expressing about the delay time. Okay, the time taken for the gate current to reach from 0 to zero point 0.9 Ig. Okay, so that means 0 to 90%. Okay, so the time taken for the gate current to reach 90% of the gate current. Okay, sorry once again, the time taken for the gate current to reach from 90% to 100% of the gate current, or the time taken for the gate current to reach zero point 0.9 Ig to Ig. Okay, I hope you can see the markings here. So this is the time for the gate current. Okay, so in terms of anode current, if I want to define means the time taken for the anode current to reach from 10% to here, sorry, look at here, sorry, to reach 0 to 10%. So actually this is the leakage current, this is the forward leakage current. Okay, so this area is the forward leakage current. Okay, so this is the time taken for the anode current to reach, okay, to reach 10% of the anode current, or you can write it as 10% of the anode current. So three definitions we have seen. So the time taken for the anode voltage to fall from 100% to 90%, or the time taken for the anode voltage to reach to fall from VA to zero point 0.9 VA. Okay, or else if you want to define in terms of gate current means the time taken for the uh, gate current to reach from zero point 0.9 Ig to Ig. Okay, so here it is rise. Okay, here it is fall, voltage is falling, and the current is rising here. Okay, I mean the gate current, of course it's an external source. And look at this anode current. In terms of anode current, if we want to define, means the time taken for the anode current to reach 10% of the anode current. Okay, or I mean 0.1 IU. Okay, so that's about the delay time. Okay, so the name itself indicates there is some delay to reach the time taken for the particular parameter. I mean either it may be a voltage or current, so to reach certain value. Okay, so immediately within a zero time it cannot reach there. Okay, so that is a minimum transition time. Okay, next another parameter is, another interval is rise time. So I hope you can define easily now. So rise time also we can define in terms of anode voltage, anode current and gate current. Okay, so look at the interval here. So if we want to define from anode voltage, okay, so this is the anode voltage. So initially it is 90% of anode voltage, that means 0.9 va to 0.1 va. So the time taken for the anode voltage to fall from 0.9 va to 0.1 va. Okay, so that is the rise time. Or in terms of anode current, if you want to define, means the time taken for the anode current to reach from 10% to 90% of the anode current. Okay, so the time taken for the uh, 1 second. Okay, so the time taken for the anode current to reach 10% to 90% of the final value. So final value in the sense the anode current. Okay, so this is how the anode current is rising. So here what we are going to assume here in the sense, what is going to happen here in the sense, when the gate current is applied. Okay, so when the gate current is applied here, the anode is the anode and cathode, earlier the voltage is applied between these two terminals, so it is in blocking state. Now what happens, the current slowly starts rising because of this gate current. This junction J2, the layer gets increased here. That means actually here this J2 comes slowly into the reverse bias. That means it comes into the forward biased condition. Earlier it is reverse bias, and this behavior gets reversed. That means it comes back to the forward biased condition. So junctions J1, J2, J3 will be completely forward biased at the last stage. Okay, that means at the final state. So since all the junctions are forward biased, there will be maximum current will be flown between these terminals. That means from anode to cathode, the current will be flown. So maximum current will be flown. So when the J2 is partially or some amount of carrier is completely, when it is not come into the forward bias, so a small amount of current will be allowed. So that is how it is behaving. Okay, so that is the control achieved with the help of the gate terminal. Okay, so look at here. So look at the first figure. So after the uh, when it reaches to the rise time, the gate current is stopped there. That means this junction J2 is forward biased, so all the maximum amount of current is uh, flowing through the anode and cathode, through the anode to cathode. Okay, so then after that there is no need of any gate current here, because uh, this is a very minimum current here which is required to turn on the switch when once the switch is completely closed. Okay, once the switch is completely closed, so there this gate current is not at all helpful in controlling the current or any parameter here. I mean the current is not controlled here. Okay, so once the switch is completely closed, it is no more able to control the switch. So that is also one of the drawback of the SCR. Okay, so this is the major drawback of the SCR, because this gate terminal is used to control the parameter when the switch is completely closed. So this gate terminal is not at all helpful in controlling the switch. Okay, so that is the major drawback of the SCR. So for that only we have gone for the GTO, gate turn off thyristors. Okay, okay, so that's that we'll discuss later. Now just look into the spread time. Okay, so spread time means it is defined as TP. Okay, so again we can define in terms of anode voltage and anode current also. So, and forget about this gate current because it is over. So once the switch is almost reaches to 90%, so this gate current is no longer existing. Okay, so no need of this gate current also because all the junctions are forward biased. Okay, right. So this spread time, it can be defined as the time taken uh, for the anode voltage in terms of, if I want to define in terms of anode voltage. Okay, so the time taken for the anode voltage to fall from uh, finally to reach to 10% of the anode voltage. So actually here uh, you can define as almost all zero, but this is the forward voltage drop. Okay, because it will be around 1 to 1.5 volts actually. So what we have seen in case of the diode also, so there exists a small amount of voltage drop. So practically we can treat it as a zero also, but it is mentioned on state voltage drop across SCR. I hope you can see here. So this is a very pinch of voltage there. Okay, it will be around 1 to 1.5 volts. Okay, so that's the case. And if I want to define in terms of the anode current, okay, so how can we define the time taken for the anode current to reach from 90% to 100%? So what is 100% in the sense IA? Okay, or else you can define as the time taken for the anode current to reach zero point 0.9 IA to IA. So that is the load current. So why we are calling it as load current means when the switch is completely closed, what happens? The maximum current, I mean the load which is connected through this switch, it draws the current. So it depends upon the load or the external circuit. Okay, so the maximum current is flown through the switch. So here this is the complete turn on time. So this is the complete turn on turn on time of the SCR. Okay, so now which was earlier it is in a forward blocking state, now we have brought this switch to completely turn on, that is a forward conduction state. So this is the complete behavior of this this is the turn on behavior of this SCR. Okay, so initially it is forward blocking state, now we have brought it to the forward conduction state. Okay, and we have noticed the I mean in terms of anode voltage, gate current and anode current. In terms of these three parameters, we have defined delay time, rise time and spread time. So the combination of delay time, rise time and spread time gives the total turn on time. Okay, here it is completely turned on and it exists for a short period. I mean it depends upon the circuit operation and it exists. Okay, so this is the complete turn on behavior of the SCR. Okay, so now let's look into the turn off characteristics of this SCR. Okay, so now we have brought this forward blocking state to forward conduction state, and now again we have to analyze this forward conduction state to forward blocking state. Okay, I repeat once again. So we have to bring this forward conduction state to forward blocking state. Okay, so that process is nothing but commutation process or turn off process. Okay, so bringing back the SCR or bringing back the switch or bringing back this thyristor from forward conduction state to forward blocking state is called as the turn off process or commutation process. Okay, now as I said you before, once the switch is completely closed, so there is no control over this gate terminal, it is no more helpful. Okay, so then how can we bring back this forward conduction state to forward blocking state means either we have to uh, interchange the polarities or either we have to reduce the voltage. Okay, so that means uh, this anode is fed with negative or cathode is fed with positive. Okay, or else by reducing the input voltage. So any of these methods we have to go through, and practically it is not appreciable. Okay, so that is the reason why they go for the commutation circuits. Okay, so which will be discussed further. So that is nothing but the external circuit we use to bring back this forward conduction state to forward blocking state. Okay, so that is the drawback of this SCR as discussed before. So okay, fine. So we go for the interchange of this supply voltage. Okay, that means anode is fed with negative and cathode is fed with positive. So then it comes to the reverse biased condition. So when it comes to the reverse bias, in the sense, what happens to these junctions J1, J2, and J3? So earlier, all the junctions are, I mean, majorly these junctions J1 and J3 are forward biased earlier, and now it has to come to the reverse bias condition. So normally, so forget about all these things. So normally, so what about this layers, and what about this junctions behavior means when it is in when it is in reverse bias condition means. Okay, so junctions J1 and J3 are reverse bias and J2 is forward biased. So that stage has to be appeared here. Okay, so right. So again, as segregated or as divided in the turn on time. So it is a combination of delay time, rise time, and peak time. So here also, so the turn off process, in this turn off process, so it is segregated into different intervals. Let's look into one by one. So here it is reverse recovery time. So where TRR is the reverse recovery time, gate recovery time, or it is called as the recombination time period, and TRR is the I mean, here you can see T1, T2, T3. So this is the total time for recovery, and T3 to T4, it is the total time for recombination. So recombination of the charge carriers actually. So here I'm not going in detail of the charge carriers part. Okay, so just I'm giving a brief up of these time periods. So where TQ is the total circuit, uh, sorry, so and here you can see this reverse voltage due to the power circuit. See, this is the total turn on time, and here we are going to apply the reverse voltage. So that means anode is fed with negative and cathode is fed with positive here. Okay, so this reverse voltage is applied. Okay, so then what about its behavior? So it is also resembles like a diode reverse recovery characteristics, right? So likewise, so this is the total time period required for the SCR, that is the interval is T1, T2, T3. Okay, so this is the total time period required for its recovery. Okay, because these junctions are the width of these junctions, that means the charge carriers has to lessen there actually, that means the layer width has to be reduced. Okay, that means it has to come back to its normal state. So what it is how it is behaving in the reverse blocking state, that means J1, J3 are reverse biased and J2 is forward biased. So this layer has to be thinner. That means initially, based on the I mean, its behavior. So earlier it is in forward bias. So here uh, the layer has to be reversed here. So it takes some time to uh, come to the reverse biased condition. Okay, so this is the total time period required for all the layers, that majorly J1 and J3. Okay, because these two are directly at I mean this layer P layer. So here you can see this P layer is fed with negative and this N layer is fed with positive. So majorly first these junctions J1 and J3 has to be reversed there. So this is the total time required, and TGR, so is the gate recovered or the recombination in the sense. So this J1 and J3 completely reverse bias. That means it comes to the normal state. Their charge carriers are comes to the normal state. So that is the total time required. Okay, so where TC is the total circuit turn off time. Okay, so the switch turn off time is different from this total circuit turn off time. So that is the difference between TQ and TC. Okay, so that is the case. So that's about the turn off time of the SCR. Okay, so and here it is, and the last figure here, it gives the power losses. So during the turn on only, so the maximum amount of current is allowed, so that the heat absorbed in the form of heat only. So for that also we use some heat sinks there. Again we use some circuit elements there. So here the power loss is majorly is observed during the turn on period, because the maximum amount of current is flowing through that turn on period. Okay, so that's why we can see the power loss during the turn on time. Okay, so this gives the steady state operation. That means the switch is completely closed here. Okay, here the current slowly rises. So because of this, we can see some amount of losses there. So we have to focus on the heat also, because when the temperature is higher, so the switch behavior also gets reduced because it deteriorates. Okay, so for that we need to provide some heat sinks, or some other cooling methods are also used for the absorbing this heat. Okay, or else the behavior of the switch, it gets deviated, because these layers, I mean these layers behavior also changes. Okay, so that's all about the switching characteristics of SCR. So hope you have understood this. So thank you.